Hello everyone, welcome to this lecture in the Neural Networks from Scratch series. Today, we are going to learn about an important optimizer for neural network training, and that optimizer is called as ADAGRAD. Eventually, ADAGRAD led to the development of the optimizer ADAM, which is now used commonly in most modern machine learning frameworks. So, to really understand the ADAM optimizer, first we need to understand the basics of the ADAGRAD optimizer. In many modern machine learning settings, ADAGRAD is not used nowadays, but still the concepts which ADAGRAD teaches us are very important, and that's why it's necessary to learn about this optimizer. In the previous lectures, we have looked at gradient descent with momentum, and we saw that when we use momentum, we really get an accelerated convergence, which means that we reach towards our minima in a much faster way with very less number of oscillations. So, momentum actually helps us to reduce the oscillations. And we saw that with momentum, the accuracy of the neural network training is very high and the loss is very low. Essentially, the way momentum worked is that it also gave importance to the previous weights. But the key thing to note in the momentum, if you look at the weight updates, of course, the weight updates depend on the previous weight updates. But if you look at the learning rate alpha, this is a common shared learning rate among all the weights. So all the weights of the neural network use this same alpha, and that alpha decays with time. So we specify a learning rate decay, and as the iterations go on proceeding, alpha goes on decreasing with time. This is to make sure that we start off with a high step size and we explore the entire loss landscape, but later the step size goes on reducing so that when we settle in places close to the global minima, we don't keep on oscillating. The key thing which I want you to notice that in momentum, there is a common or a shared step size among all the weights. Although it is decaying with time, it is the same step size which all the weights use. This is the key idea upon which ADAGRAD operates. The main premise or the main concept of ADAGRAD is that okay, why do all the weights essentially have the same learning rate? Why is there a common learning rate across all the weights? Why can't the different parameters or the different weights of a neural network have different learning rates? And this is a very key concept to understand. So the first thing which we will look at is that how does it help us if different weights have different learning rates associated with them? Let's look at a neural network like this. This is a neural network which has two inputs over here. It has three neurons in the first layer, and it has three neurons in the output layer, which are then used to calculate the loss. In the first layer, every neuron has two weights associated with it. So there will be six weights in the first layer. In the second layer, every neuron has three weights associated with it, and there are three neurons. So there will be nine weights in the second layer. In the first layer, there are three neurons, so there will be three biases, one corresponding to each neuron. And in the second layer, there are again three neurons, so there will be three biases, one corresponding to each neuron. So essentially, there are 6 plus 3 plus 9 plus 3, which is 21 different parameters here. And Adagrad says that all these parameters should have different learning rates for better performance. Let's see why do we need different learning rates for different weight parameters. So I am going to take a simple example here, which is something like, so let's say if we have just two parameters w1 and w2, and the loss function is a function of w1 and w2 given by this formula: w1 square by 100 plus w2 square is the loss. Okay, if you plot this in a two dimensional landscape, the contours of the loss will look something like this. Since there is a factor of 100, we have the loss function which is hugely stretched in the horizontal direction, but which is not very stretched in the vertical direction. So W1 is my x-axis and W2 is my y-axis. So let us do some calculations. Let us take W1 equal to 1 and W2 equal to 1. It will probably lie somewhere around here, 1 comma 1, right? And I want to find the partial derivative of loss with respect to W1, and I want to find the partial derivative of the loss with respect to W2. So let's find the partial derivative of loss with W1. When we do this, W2 will be treated as a constant. So we'll just take the derivative of this term with W1, which is 2W1 divided by 100. And since W1 is equal to 1, the partial derivative of loss with respect to W1 is 0.02. Now let us find the partial derivative of loss with respect to W2. When we do this, the first term has W1, so it will be treated as a constant. So all we need to do is find the derivative of this term with W2, and that is just 2W2. Since W2 is equal to 1, the partial derivative of loss with respect to W2 will be equal to 2. Now I want you to compare these two partial derivatives. Partial derivative of loss with respect to W1, which is 0.02, and partial derivative of loss with respect to W2, which is 2. So you will see that partial derivative of loss with respect to W2 is 100 times greater than the partial derivative of the loss with respect to W1. What does this mean? It means that if we make small changes in W1, it would not increase or decrease the loss too much. But if we make small changes in W2, that will be 100 times more significant than changes in W1. What does this tell you? Let's say if we are doing the gradient descent and we are updating W1 and W2. So let's say we are using the same step size to update W1 and W2. Then both W1 and W2 will be updated by alpha times. So W1 will be updated by alpha times partial derivative of L with respect to W1, and W2 will be updated by alpha times partial derivative of let me write this again, partial derivative of L with respect to W2. So W2 will be updated by uh, this value. Now, since partial derivative with respect to W2 is so high, you will see that W2 will change by a huge amount. But if and partial derivative of L with respect to W1 is very low, so W1 will not be changing too much at all. This would indicate that some weights will change very fast and some weights will change in a very slow manner, and this is not very good at all. In fact, this can lead to uh, non convergence of the loss, because one weight value will not update at all. Ideally we want normalization, which means that all the weights are updating on the same scales. We do not want one weight to be updating very very quickly, and we do not want the other weights to be not updating at all. If some weights are not updating, it means that that neuron is not contributing anything. It's like a dead neuron. Since we want all the neurons to be contributing, ideally what we want is that if partial derivative of L with respect to W2 is so high, then why don't we make the alpha associated with it? So let me mark it with a different color. If the partial derivative of L with respect to W2 is so high, why don't we make the step size or alpha associated with it to be very low, so that the change is same? This can also be represented as, if the partial derivative of L with respect to W1 is so low, why don't we make the step size associated with it high? So let me call this alpha 2 and let me call this alpha 1. So ideally what we want is that we want alpha 2 to be much much smaller than alpha 1. So ideally we want alpha 2 to be much smaller than alpha 1, because the partial derivative of L with respect to W2 is much higher than the partial derivative of L with respect to W1. So to put it in another words, the step size for W2 should be smaller than the step size for W1. This can also be described as follows. Higher the parameter derivatives, smaller should be the step size. So if the parameter derivative is very high, the step size should be small. And if the parameter derivatives are small, then the step size should be large. This is what we ideally want. And that's where the concept of ADAGRAD comes into the picture. What ADAGRAD says is that we don't want one weight to be updated much faster than the other weights. That would lead to some neurons being inactive or dead neurons. We want all neurons to be contributing. So the step sizes should be in accordance with the parameter derivatives. If the parameter derivatives are high, the step sizes should be small. If the parameter derivatives are small, the step sizes should be large. I hope you have understood the intuition behind ADAGRAD. Now I'll move to the second part of this lecture, which is the mathematical procedure for ADAGRAD. And in the third part, we will look at how to code ADAGRAD in Python. So, okay, we know intuitively what we want to implement. We want the step size to be inversely proportional to the parameter derivative. Higher the parameter derivative, smaller the step size. Smaller the parameter derivative, larger the step size. That's what we want. So the way ADAGRAD is implemented in practice is as follows. First, for every given parameter, we maintain an history of the previous gradients of that parameter. Note that as the iterations are proceeding, the gradients of the loss with respect to a parameter go on continuously changing, right? So there is a history of these gradients. So we maintain this history in this variable which is called cache or cache value. So what this cache will do is that let's say we start out with the iterations, the cache will be set to 0. In the next iteration, the cache will be set to the gradient of the parameter whole square. And in the next iteration, the cache will be the previous cache value plus the current parameter gradient the whole square. So basically, to find the cache value at a given time point, you add the parameter gradients of all the previous iterations with the current iteration. That's how you find the cache value. So the main thing to note here is that we are storing a history of gradients, and we are not just storing the gradient value, but we are storing the value of gradient square. And I will tell you why we are doing gradient square in a minute. But for now, just keep in mind that we are storing the history of the parameter gradient values or the partial derivative of the loss with respect to that parameter. So let's say we are in the fifth iteration. We will find the partial derivative of the loss with respect to weights in the current iterations, square them, and we will keep that. So that will be this term, parameter gradient whole square. But we will add this with the summation of all the previous gradient values, because that will be stored in the cache until the fifth iteration. The reason we store this cache value is because that will be used in the parameter updates. Remember that when we did a normal gradient descent, we just used this for the parameter update. We took a weight which is W, and then we updated the weight like this. The new weight is equal to original weight minus alpha multiplied by parameter gradient. This was the original gradient descent update. So in the original gradient descent update, we only take alpha into a multiplication of parameter gradient. So this part of the update is the same. But what is new in the ADAGRAD is that we divide this by the square root of cache value plus epsilon. And remember, the cache value is the summation of the parameter gradient whole square. So let us understand the two terms of the denominator, cache and epsilon. The reason this cache term is in the denominator is that if the cache is high, which means that the parameter gradient values are historically very high, not just in the present iteration, but in the past iterations also. And if that is the case, we need the step size to be smaller. So that's why we are dividing by the cache. So higher the cache, smaller is the effective step size since we are dividing by it. And if the cache is smaller, it means that the gradients are small. So the step size can be larger. and that's why we have put this cache in the denominator. So higher the cache, higher the gradient values, smaller is the effective step size. Smaller the cache, smaller the gradient values, and larger is the effective step size. And the reason we add this epsilon is that epsilon is a very small quantity. It's basically a hyperparameter which is added just to prevent the division by zero. So in the initial iteration, cache value is equal to zero. So for some reason, if the parameter gradients are all zero, we don't want to divide by zero, right? So that's why we add epsilon. So now, did you understand why did we do a parameter gradient square in the cache calculation? The reason we do a square here is that to prevent taking the square root of negative values. So when we do the parameter gradient square and then add it with epsilon, uh, it automatically means that the denominator is a positive value. So taking the square root will result in a valid answer. So we are going to update the weight values by this particular formula. So when we write it in practice, it will look like the new weights will be equal to the old weights minus alpha times the parameter gradient divided by square root of cache plus epsilon. So parameter gradient is just the gradient of the loss with respect to the parameter at the current iteration, and cache will effectively be accumulated squared gradient up till that point. So for that particular parameter, if the accumulated square gradient values are very high, we need to have a smaller effective step size, and that will be ensured since square root of cache is in the denominator. On the other hand, if the accumulated square gradients up till that point are very small, then the square root of cache will be small, and so the effective step size will be large. This is exactly what we wanted. If you look at these pieces of text over here, we wanted the higher the derivative, smaller the step size, and smaller the derivatives, larger the step size. By including this cache term in the denominator, we ensure that. When we move towards the code, let me tell you the general values for alpha and for epsilon. So alpha value is generally taken to be 1. So this is actually alpha with decay. So this will be something like here. So we are going to use a learning rate decay, and the initial step size for this ADAGRAD is usually taken to be equal to 1, and then we will use a decay rate of 0.001 or 0.0001. That's the typical value which is used in practice. The epsilon value is usually used as very small, 10 raised to minus 5, 10 raised to minus 6, etc. I'll show you what these values are in the code. But for now, I just want you to intuitively understand why do we do a square root? Why do we divide by the cache? And if you think about it, we could have just replaced the cache with the current gradient whole square, right? Why do we need to take the history into account? Why are we accumulating the gradients? The reason we are accumulating the gradients is because we also want to know whether that parameter has high gradients in the past. If it has high gradients in the past, we also want to ensure that still the step sizes should be smaller. So we are not only looking at the current gradient of the parameter, we are also taking into account its past gradients as well. Before moving into the code, we can do a practical demonstration of how the cache value actually accumulates. So let's say we start, let's say there are 10 iterations and we are looking at one particular parameter which is called as W1. In the first iteration, the gradient of the loss with W1 is zero point 0.5. In the second iteration, the gradient of the loss with W1 is zero point 0.5. And this same thing continues till the 10th iteration, where the gradient of loss with respect to W1 is zero point 0.5. Now let me show you how the cache value accumulates. Initially the cache starts with 0. So the cache is denoted by capital G. G0 is 0. Then remember, to calculate the new value of cache, we add the old value of cache plus the current gradient square. So capital G1 will be G0 plus G1 whole square. Small g1 is the current gradient, which will be 0 plus zero point 0.5 square, which is 0.25. This is the first cache value. The second cache value is the previous cache value g1 plus the current gradient, which is small g2 whole square. So this will be 0.25 plus zero point 0.5 square, which is zero point 0.5. Similarly, when we reach to the 10th cache value, this will be capital G9, which is the previous cache value, plus small g10 whole square, which is the current gradient whole square, and this value will be equal to 2.5. So when we are going to do the weight update, the W1 weight update at the 10th iteration, ideally what we will be doing is we will be just doing W1 equal to W1 minus alpha into 2.5 for normal gradient descent. But now we will divide it by square root of cache value plus epsilon. So since we did 10 iterations, the cache value is 2.5. So that's why we are dividing it by 2.5. Okay, so this is how it is simply used in practice. We just accumulate the sum of the squared gradients and we divide it by the square root plus epsilon. I also want to highlight one disadvantage of the ADAGRAD method because of which it did not become too popular. See, we are doing 10 iterations here, right? And the cache value has already reached 2.5. If we did 100 iterations, so if we did 100 iterations, you will see that the cache value actually reaches uh, a value of 25. If you actually do 10 raised to maybe 5 iterations, you will see that the cache value actually reaches to 5, 0, 0 and 0, 25,000. Do you see the problem which will happen if the cache value reaches 25,000? What will happen is that if we divide by 25,000, this whole part will be very, very small. So that means that the weights will not get updated at all after those many number of iterations. So after 10 raised to 5 iterations, the weights will not get updated at all. That is the main problem with ADAGRAD. What's happening is in ADAGRAD is that the cache value is continuously increasing, right? Because we are updating the previous, we are adding the previous gradients. So the cache value is continuously increasing, which means this denominator is continuously increasing. So if we reach the a particular stage, let's say at 1000 iterations or 10,000 iterations, where the denominator value becomes very high, the weights will not get updated at all, and so the learning will stagnate, the learning will not improve at all. This is the main disadvantage of the ADAGRAD optimizer. Please keep this in mind because sometimes this question is asked in interviews as well. So one of the main disadvantage of ADAGRAD is that in the cache it keeps on accumulating the sum of gradients, so the cache will keep on increasing. Now as we reach very high number of iterations, the cache value can become very large. That might make the denominator very large, so the step size effectively will become very, very small, and so the weights won't update at all. Our learning will stagnate, and I demonstrated this to you via numbers. If we have 10 iterations, the cache will be 2.5, but if we have 100,000 iterations, the cache will be 25,000. So imagine dividing by square root of 25,000. Already it will be a very small, the effective learning rate. So the learning will stagnate. Okay, so now I hope you have understood the intuition behind the ADAGRAD optimizer and also the mathematical equations which govern the ADAGRAD optimizer. We are now going to jump right into the Python code where I'll be showing you how to implement the ADAGRAD optimizer class and also running our code on a specific data set. So before jumping to the ADAGRAD optimizer, let me show you the data set which we are using in our example. So this is the data set. Every point on this data set has two attributes, x1 and x2, and it belongs to either of the three classes, red, green or blue. Our goal is to design a neural network. So our goal is to design a neural network which looks something like this, to classify correctly which color a point belongs to. So let's say we have optimized the weights and biases of the neural network, and if I give it a new data point, the neural network should tell it correctly whether it's red, green or blue. So that's the problem which we are considering. And now let me jump towards the ADAGRAD piece of code. Okay, so first we'll define the optimizer ADAGRAD class. And in this class, there are different methods such as init, pre-update params, update params, and post-update params. Let me explain each of them. In the init method, this method will be automatically called when an instance of this class is created. What will happen in this method is that we will keep track of some parameters. So for example, as I told you, we will use a learning rate decay, right? So the decay parameter by default is 0. It will keep track of that parameter. It will keep track of the learning rate alpha naught. So remember, let me take you to the decay formula again. So the learning rate decay formula is this: alpha naught divided by 1 plus learning rate decay into time. So there are two parameters here: the initial step size and the learning rate decay. So by default, we start with an initial step size of 1 and a learning rate decay of 0. And in this method, we are also tracking the current learning rate. So the learning rate will be changing with time, right? According to this formula over here. So we are tracking the current learning rate here, and we are also tracking the iteration number which we are on. The reason we track the iteration number is because the learning rate depends on the iteration number. Higher the iteration number, smaller the learning rate. So these are the parameters which we are tracking. We are also tracking epsilon. This epsilon is used in the ADAGRAD denominator, and I showed you that over here. So you can see we add an epsilon in the denominator, and the epsilon value is very small, 10 raised to minus 7. We usually don't change this value after defining it. Then before any parameter updates, we first update the learning rate. Remember, the learning rate is changing at each iteration according to alpha naught divided by 1 plus decay rate into the number of iteration we are on. So that's why it's important to track which iteration we are doing right now. The current learning rate will be very important because when we are going to use this formula for ADAGRAD, this alpha which I'm denoting here by a green color is the current learning rate. Okay, and then the most important piece of this class is the update params method. So what will happen in this method basically is that it will first create two arrays: weight cache and bias cache. Those will all be initialized to 0 right now, and the size of these arrays will be the same as the number of weights and the number of biases, because remember that for each weight we are maintaining the cache. uh, okay, and so what we will be doing here currently is that the cache value, we will be taking the previous cache and adding the parameter gradient square, right? So that's exactly what's written here. For the weight cache, we'll take the original cache. So plus equal to means we'll take the previous cache and then add the partial derivative of loss with respect to weight whole square, which is the current gradient square. Similarly, for the bias cache, we'll retain the previous bias cache and then add the partial derivative of the loss with respect to the bias whole square. And then what we will be doing is that using these cache values, we'll be updating the weights and the biases. So the new weight is equal to the original weight minus alpha, which is the current learning rate, into the partial derivative of loss with respect to w. Up till here it's the same as normal gradient descent, but then we divide by the square root of cache plus epsilon. This is exactly what we saw over here: alpha into gradient divided by square root of cache plus epsilon. And when you look at the bias part, it's the same. You take the bias and you subtract alpha into gradient with respect to bias, and then you divide by the square root of bias cache plus epsilon. Note that in the whiteboard, I always mentioned about weights, but the same logic and the same discussion holds equally well for the biases as well. So this is how we'll be updating the weights and the bias in the method called update params. And then the final method here is the post update params. What will happen in the post update params is that we'll just increase the iteration count by 1, because we have updated the parameters in that iteration, and then we'll move to the next iteration. Whenever we move to the next iteration, remember that the learning rate will change since we are at a different iteration, and then we'll update the weights and biases according to the similar formula which we discussed over here. So this is the optimizer class and we will be calling it in the neural network. So now I'm going to show you how to apply the ADAGRAD class in practice on a practical problem. So we are going to be looking at the spiral data set which I showed you before, where there are points who belong to either of three classes, red, green or blue. So I'm going to take 100 samples of that data set, and this is the neural network I am going to construct. I'll have one layer initially which has two inputs because every data point has two attributes and 64 neurons. Then that will be having a ReLU activation. Then the output of the ReLU activation will be chained with a second layer. The second layer has 64 neurons and it has three output neurons. Those output neurons will go through the softmax activation, and then I will get either red, green or blue classification. That's why we have three output neurons. And then we will have the categorical cross entropy loss, since this is a classification problem. Okay. Now I'm going to use the optimizer ADAGRAD, and the decay rate which I'm going to use is 10 raised to minus 4. Uh, so these are the parameters. If you look over here, if we don't specify the decay rate, it would have started with 0. And I'm going to use the default alpha naught, which is 1, and epsilon as 10 raised to minus 7. So I have initiated an instance of the optimizer class over here. Then I'm going to perform 10,000 iterations of the forward pass, and I'm going to perform the backward pass as well. So first we'll do a forward pass through the first layer. The output of the first layer will go through the ReLU activation function. The output of the ReLU activation function will go through the second layer. The output of the second layer will go through softmax, and then we'll find the loss, the cross entropy loss. In this part of the code, we are just printing the accuracy, and we are printing the epoch number, the accuracy, loss, and the learning rate at each epoch. Remember, one epoch is basically one cycle through the entire data set. Of course, we'll need to do the forward backward pass because it is here that we'll be maintaining the partial derivative of the loss with respect to the inputs, weights, and biases of every layer, which will be needed to update the weights and biases. And the update rule is specified over here. The update rule is specified like this: weights new equal to weights old minus alpha times the gradient divided by square root of cache plus or cache plus epsilon. Okay, so we'll do the backward pass. We'll start right at the end, then we'll do the backward pass, then we'll do the backward pass through the second layer. This will give us the partial derivative of the loss with respect to the inputs, weights, and biases of the second layer. Then we'll do a backward pass through the ReLU, and then finally we'll do a backward pass through the first layer. This will give us the partial derivative of the loss with respect to the inputs, weights, and bias of the first layer. Now that we have all the gradients, we can essentially call these four methods: pre-update params, update params, for both layers, layer 1 and layer 2, and then the post-update params. The reason we call the update params for both layer 1 and layer 2 is because we want to update the weights and biases in both of these layers. And the way we are updating it is based on the ADAGRAD formula which we saw. And then we'll call the post update params because we are going to track the iterations, since that will determine the current learning rate. That's it. So if you think of the code, first we create an instance of all the classes, then we call the forward pass, then we call the backward pass, and then we call the methods of the optimizer, so that we tell the code how do you update the weights and the biases. So basically what's happening in these four lines is that every weight or bias is getting updated by its own learning rate, which is determined by the cache value which it is storing for that particular weight or bias. Now I'm going to run this piece of the code and let us actually track the epoch and the accuracy. So here we can see that around 1500 epochs the accuracy is zero point 0.7. Now the accuracy is slightly stagnating, as you can see, to zero point 0.7, but it's again going up. It's 0.86, 0.85, 0.86 again. And as you can see, now we are at around, I think, 7500 epochs and the accuracy is 0.887. And now it is not changing at all. In fact, it's only slightly increasing. And now the final accuracy is 0.893. So keep this final accuracy in mind, and I want to now compare to previous accuracies. So for the SGD with momentum, we got a accuracy of 0.953, which is definitely much higher than ADAGRAD. In ADAGRAD right now, when we ran the code, we got an accuracy of point uh, 893. So that's an indication that the SGD with momentum might sometimes yield better results than ADAGRAD. Now let's compare with just the learning rate decay. So if we just used a learning rate decay without uh, anything, so without ADAGRAD or without momentum, then we can see that the accuracy was around 0.717, which is much lower than ADAGRAD. So one thing is for sure is that when we implement the ADAGRAD optimizer, uh, it leads to a much higher accuracy than, let's say, we just use a learning rate decay. So what I mean by just using learning rate decay is that if we didn't have this denominator, so if we didn't have a denominator which basically gives a different step size to each parameter, the only thing we'll have is the numerator. So that's just the learning rate decay, and we get a lower accuracy in that case. So this means that adding the denominator actually helps us. So adding a individual step size or an adaptive gradient for each parameter helps us. That's number one. The second conclusion is that momentum still remains our best method. So Adagrad gave us an accuracy of 0.83 over here, but if you look at the momentum accuracy again, we had an accuracy of 0.953. So momentum still remains the best method, and that's one of the reasons why Adagrad is not very commonly used in practice. It is used, but Adam is an optimizer which is preferred the most, and we'll look at Adam in one of the subsequent lectures. Now I just want to show you a video of this exact same code optimization which we did right now, so that you can understand the training much better. So I'm going to play this video right now. Okay, here you can see that the training is proceeding right now, and I want you to look at the background. So the background color is our prediction, and these dots are the true value. So you can see it. So let me play it till the end. Now it has almost stagnated. So I'm going to stop over here. Okay, so let's look at the predictions made by this particular optimizer. First of all, let's see at this portion. So in, or let's see, in this portion, the boundary is green in color, but there are three red points which are clearly misclassified. Let's look at this point. The boundary is red in color, but this point is blue, clearly misclassified. Again here, the boundary is red in color, but this point is blue, so misclassified. It has a good accuracy, as you can see in the plot on the right. It has an accuracy of around zero point 0.8, which is also the same accuracy which we had obtained over here. But there are some mistakes which this Adagrad optimizer does. So it's not the best optimizer, but it's definitely much better than just using a learning rate. So this actually brings us to this lecture on Adagrad. In the next lecture, we are going to be looking at another optimizer called RMS prop, and then using Adagrad and RMS prop, we'll have a lecture on the Adam optimizer. Thank you so much, everyone, and I look forward to seeing you in the next lecture.